Bismillahirrahmanirrahim. My name is Arman and I'm a data science student at IBA Karachi. And in this video, I'm going to demonstrate about my MS project. So the objective of this project is to build an anomaly detection framework in order to solve various problems in different industries like network industries where cyber attacks frequently happens, and in healthcare sectors where different kind of diseases they need to monitor it. So we are trying to find a method through which we can monitor the real-time anomalies. In order to build this framework, we used Gaussian mixture model. A Gaussian mixture model is a probabilistic model in which we can answer the data in probabilities rather than answering in a rigid form or a hard clusters. We use soft boundaries and we answer the data in probabilities, and it is considered to be a good approach rather than a deterministic models. So we use this approach, and this model basically runs over the algorithm, which is a very famous algorithm that is expected maximization. That there are two components. The first one is expectation and maximization. um, the main advantage here is it learns the joint probability distribution of the training Gaussian by iteratively enhance the likelihood of the data. So at the first step, it basically measure the probability of each data, and at the second step it maximize the likelihood by keep changing the parameters, and it enhance the likelihood of the data, and which best fit the data. So this is the general background of this project. And the idea is that we are assuming that the anomaly size is very small, and the normal data is very huge in size, and we are using this approach for multivariate data. So in multivariate data, it's very complicated to detect a small variation in the data. So that's why we use a density based approach, which is Gaussian mixture model. So the framework basically works on this five steps. The first one is pre-processing. We assume that the data is containing labels because we are we are trying to build a proactive approach. We have some reference outliers to measure the performance. So we build this data and we pre-process it for for the model, and the second step is training the model. Gaussian mixer model training is a bit tricky one, and the model performance depends on the hyperparameters, and the hyperparameters obviously depends on problems to problems. So we have experimented different data sets. We have worked on several outliers data where the class imbalance was extremely difficult to monitor. So training depends on different parameters, and uh, and uh, and uh, and uh, selecting of the parameters depends on the data. uh, Gaussian mixture model needs two parameters. The first is the number of components, which can be taken from an elbow chart. An elbow chart is basically drawn between number of components and the Bayesian inference criteria. The Bayesian inference criteria is basically a support element for catching your number of optimal components. um, it basically add the penalties to the Gaussian parameters, so it can enhance the performance and minimize the overfitting. The third step is testing the outliers, and testing the outliers means that we train our model on the inliers, and we pass the data pass the testing data to measure the performance of the uh, model. We check where the outliers fit and where they have segregated, and the fourth step is to find the uh, Gaussian of interest. And the Gaussian of interest means that wanted to maximize the purity of outliers. We wanted to force them to settle into a single cluster so that we could have a clue, we could have a confidence interval that this mixture has a strong evidence of being an outlier. So that's the crux of this framework. And at the end, we validate our framework by using a statistical method, and we used Mahalanobis distance, which is basically used to calculate uh, statistical distance between two statistical objects. Here we are calculating the distance between Gaussian components, which we have previously learned, and the distance between outliers. And it is used for multivariate data. Okay, now let's discuss the application of this Gaussian mixer model. So basically, we have chosen different data sets from UCI repositories to claim our hypothesis that we wanted to find the required Gaussian, where we can have a high probability of labeling our outliers. So for this we use different data sets, and I have built these different Python files. And let's discuss first one, and then I will show the rest of one. So this is taxonomy domain data, which is basically a forest data in which different kinds of forest and anomalies of the quantities observed. So you can see there the class imbalance is too much class imbalance, and this is the normal, and this is the normal data sets. And these are the helper function which I have used to pre-processing and plotting some visualizations. And you can see how uh, difficult it is to handle this small chunk of outliers, and this problem is already a multivariate problem. So the idea is we wanted to uh, to separate this outliers and minimize these components, because we cannot we cannot find a fish in a huge ocean. So we wanted to compart it into the small segments, so have a s- we can have a very solved and um, easy problem. So that's why we are using GMM model here. So first, before going into training, we separate the data into inliers and outliers, and we train and test our data uh, on Gaussian mixer model. The training set is also inliers, and the testing is also inlier. We choose four components here because the optimum number of components can be observed from this chart. We have seen there is no such dropping in the BIC score. So that is the idea, and then we measure the performance of different outliers and inliers. So you can see in component number 0, there the outliers affinity is 0, because no outliers is going to fit in 0 component. But you can see a huge rise in the affinity of the outliers in component 1. However, we have some inliers data. That is the limitation, I would say, because we need a reference component or an anchor component, so we can have a probability of saying that this component belongs to. So we could say this is a Gaussian of interest because there's too many outliers settled in a single component, and this component is not. This is the second favorable Gaussian component for us. So anything goes into this, we would say high probability of this. So this is the performance of the testing data, and at the end we measure the statistical distance, and so this is the statistical distance of each data points of each outliers from different components. So for component 1, the statistical distance is very high, and for component for distribution 2, the statistical distance is very less. So that means that your claim is right and you are approaching towards the right direction. So this is the Python file, and we observed the same results in the other dataset. This is a medical domain dataset, in which again we can see uh, a huge class imbalance, and you can see there are a few outliers as well. And again we used the same parameters. We used 4 components here, and these are the covariance types we can use, and it also depends on the data distribution. So I'm going to share the results here. Okay, so this is again performing good because this majority of the outliers reside in a single cluster. So this is the Python files. I'm not gonna, because the video is taking too long, but I'm going to share the main part of my project, which is the because most of the time we see that we build Python files and we do not have an interactive way of presenting your results. So at the end, I try to build this web application so that every user can make their own customized anomaly detection framework, because the framework depend on the data sets. So uh, we give user an opportunity to build the data by their own self. So this is the web app display. So this is basically a small icon which shows that the data size of the anomaly is very small, and we have already put this data, like we have seen there are 3 notebooks, so which are already experienced, and we have concluded their results. So I'm choosing this data because this is the size is small and we can easily run here in a small demo. And now I have this opportunities to see the basic EDA of the data. uh, this is the, if I check it, and I'll see the data, and you can see that there are 5 columns and 1 label, and you can see there are 7,200 rows and 7 columns. And if I want to view this data at PCA, I applied PCA layer here because I wanted to visualize the data. So if I check visualize button, and you can go and just visualize the scatter plot at a very quick way. And if you wanted to check the class imbalance, you can just check it, and you can pick the column where the label data reside, and you can have to check what is the value of your outlier data. So I built this in a generalized way so everyone can have an opportunity to see the EDA by using this web app, because these label and these values differ from data to data. So that's why I generalize this and automate this web app. So this is the initially you can see the 7.4% outliers data, which is very again very less. And I have also provided the guidelines to train your model, because as I told you that the objective is to maximize the likelihood of the outliers data, that which means that maximum data should reside into a small component, so we can claim it. So these are the guidelines I provided. Okay, how do we select the hyperparameters? We will show in few minutes. So this is the training phase, where I will split the data into 30-60 ratio. Let's split it. I have provided a slider here as well, and once it will select, it will show you the guideline for optimal number of components, because as we know, Gaussian mixture needs two hyperparameters. So this is an elbow chart. Pick the elbow of the curve as the number of components to use. So it is not visible, but you can see at 4, after 4 number of component, the BIC score um, is not going to drop. So that's why we will be taking it as 4, but you can also increase it as per your data. Select the number of components. Now we will select the components, because we have an idea of the optimum components. Now I will select the the covariance type. So I have already experienced and found that full covariance is good for this data set, because the notebook was already prepared for this data. So now I will click here to train the model. So if I click here, you can see you do not need to worry about or do not need to go back and forth. You can just see your results in a minute. So these are the results of the uh, model. So if you can see, the hard membership of training data is 85.8%, and the soft membership of the training data is 14, which is a good sign, because we can see that most of the data is reside in hard cluster, and very small data is, has a less probabilities about the cluster. And again, the testing performance is good, and the anomalies performance is again good. Anomalies are also having a very strong affinity towards few clusters. And you can see, this is the component summary, in which you can see the second component is one of the um, you know uh, the main part of the model. So we can see a lot of data points settled in component 2, and there are very few in layers. So we could have a very strong evidence of saying that this component number 2 is a very strong which can maximize our likelihood. So this is the idea. So we could in future one so we once we build this model and how to deploy it, and whenever the new row come into a system, and if this row belongs to this component, we will flag it as in potential outliers, rather than we will not saying it. If it will go into the component number 1, we could have a second highest priority of saying that this is a second type of anomaly data. But in component 0 and 5, we couldn't have so much evidence. And you can see this is the last, and the main part. This is a statistical distance, which I have shown in the notebooks, and I have displayed the display in bar chart the minimum component, which is the orange one, which shows that this is your Gaussian of interest. As we have seen, this is your Gaussian of interest, and the distance from outliers to this component is extremely minimum uh, at component number 3. So I hope you enjoyed this video, and I'll try to add more layers in this framework. Some EDA is also recommended. I know some more charts we can introduce here. Thank you so much.